So then I guess we are where we are. Yeah, okay, welcome to this introduction to kinetic fluid dynamics. So my name is Martin Geyer, and what I'm showing you has been developed and derived by many of our colleagues, Konstantin Kutscher, Stefan Lenz, Andrea Pasquali, Martin Schönherr, and Anna Wellmann. Okay, so what I'm going to talk about today is, of course, kinetic methods with a special focus on the Cumulant lattice Boltzmann method. I will show some applications, a few applications, urban ventilation and aeroacoustics, and a little bit on complex fluids, where we talk about on fire and concrete. And all of this is more or less a little bit an overview. So I show you a little bit of a teaser, and later, when you're interested, we can go on in a more in-depth discussion on this. Let's start with what we mean by kinetic methods. So there are, in principle, several ways how you could describe the physical reality, and what most of us are familiar with is that the world around us is made of atoms. Yeah, so this is so to speak. You can go to let me see whether I can actually. Yes, I can. So you can go to a Newton description where you have particles flying around, and these particles collide with each other or interact with each other. So you have an atomistic view. And what many of you do, or maybe all of you do, probably is continuous fluid dynamics. So you're solving the Navier-Stokes equation. So this is, so to speak, the other end of the spectrum. And in between this, we have something else, which is gas kinetics. So actually, the continuous description, this could be called fluid dynamics. So you solve the Navier-Stokes equation, and the kinetic and description is actually called gas kinetic. And what you see is we solve a different differential equation, namely the Boltzmann equation, while in the continuum we solve the Navier-Stokes equation. So the difference between them is that the Navier-Stokes equation is actually how to say agnostic, or ignoring the existence of atoms. So we consider everything as a continuum. And the Boltzmann equation does not consider that there are different atoms. So there are no individual particles in the Boltzmann equation, but there's particles ensembles, but they are still particles. And we regard this function f, which is the distribution of particles. So this is a description that contains more physics than the Navier-Stokes equation, because it still assumes that there are these particles, but of course they are under certain conditions, they are equivalent, and the equivalence condition is that a certain quantity, namely the Knudsen number, is going to 0. So if you take this distribution function f, which is a distribution of velocity, of particles velocity, and you take thereof some moments, so you integrate over them, so then you get the density as a 0 moment, you get the momentum as a first moment, and you get the pressure or the energy as a second moment. And the equation, and this can now be solved by the Navier-Stokes equation. So these quantities, they follow the Navier-Stokes equation under the condition that the Knudsen number is small enough, or that the Knudsen number square is going to 0. So if you are not familiar, for whatever reason, with the Knudsen number, so the Knudsen number is what we call the mean free path. This is the distance between two collisions of a particle divided by the length scale by which we regard our system. So for example, we have here a vortex. This vortex has a length scale L, and then in there, and there is this length scale lambda that gives us, so which the ratio gives us the Knudsen number, and this has to be very small, such that we come to the Navier-Stokes equation. So, and now the problem is, so physicists are of course very happy with solving the gas dynamic flow. Now for an engineer would usually say, okay, so this doesn't make sense because my Knudsen number is usually small. And when I use the gas kinetic, if I use gas kinetics to solve my engineering problem, then obviously I have to resolve this mean free path or the mean free time, so the time that a particle travels between two collisions, which is of course extremely expensive. Yeah, because this is very short. For example, the mean free path in air would be something of the order of 100 micrometers. So now there are some kinetic methods that have a certain property that is called asymptotic preservation. That means that if the Knudsen number is actually small, then you can also take the time step and the grid spacing very large, and you still solve the Navier-Stokes equation. Yeah. So basically, there is this this square here. Yeah. So where you discretize the Boltzmann equation, and discretizing means you have a smallness parameter in space and in time, and they go to zero. So you come to a discrete Boltzmann equation, and if then also the Knudsen number is getting small, you solve the Navier-Stokes equation, and you can do it the other way around. You first reduce the physical problem, make this Knudsen number small, and then you make the discretization small. And if both ways lead to the same conclusion, then we call this, I mean, if you reach the Navier-Stokes equation on both paths, then we call this method an asymptotic preserving method. And the bottom line of an asymptotic preserving method is that if you are not interested in Knudsen numbers being very large, yeah, so if you actually want to solve the fluid dynamic problem, yeah, now with a kinetic method, this is why we call it kinetic fluid dynamics, you can also make the time step and the grid spacing larger than the mean free path and the mean free time. Yeah, and actually in the same order of magnitude as if you would solve the Navier-Stokes equation directly. And this is what we are using in the Lattice-Boltzmann method. So the Lattice-Boltzmann method is uses a discretized distribution function. So now we have here indices in different direction, I, J, and K. And we stream these particles. So here's actually this is a so-called characteristic diagram where we have one direction in space and one direction in time. So usually, of course, we have three directions in space, but then I cannot draw it. And what this method does is it does particles collisions, which is indicated here by the omega ijk, and then it is streaming these distributions to a next node where there's next collision, and then there's a next streaming. So there, and this is indicated by this Lattice-Boltzmann equation. Interesting thing is that the distributions that we have are not the distributions at the times of the collision, but they are the distributions in between. So during the streaming, which is indicated by that they are stored at half a time step and half a grid spacing. And this leads to a certain change in variables. So this f with the overbar, this is the physical f in this case, and the fijk, this is the one that we have in the Boltzmann equation. And because we are not storing the data during the collision, we have to add here 1/2 a collision operator, which is in here. We have so if you write this in single relaxation time form, I'll not go into detail what this means, but this is an approximation of this collision operator, because the collision happens at a time where I don't have the distribution stored. I have to reformulate them, adding half of the collision here. And by this, I can make this explicit. So please note, here, this is an implicit operator, so because we have the f bar, which is the physical f on the left-hand side, is on the right-hand side. So it's an implicit operator. But by this change of variables, I can change this in an explicit operator. And by this, I change this physical mean free time to now a discrete mean free time, tau by delta t plus 1/2. And this allows me to, this is the magic step that makes it asymptotic preserving, because now with this change of variables, it is now allowed to have delta t much larger than tau. So now if you look again at this operator here, if you wanted to implement exactly this in an code for tau being very, very small, though you would divide by 0, yeah? But by the change of variables, you're not dividing by 0 if tau is 0, but you're dividing by 1/2. Yeah, so this makes this feasible. Okay, so the number of velocities that we need in order to solve the Navier-Stokes equation only is in between 13 and 27, but we're always using 27 in our case here. So there is some kinetic legacy. So because you could ask, why could this be better than just solving the Navier-Stokes equation? Yeah, so you have even though you have this implicit collision operator, you have an explicit algorithm. Your Knudsen number now is, if you have a small set of speeds, you assume that the Knudsen number is small and you only pay for a small Knudsen number. So it's actually the same costs, more or less, as the Navier-Stokes equation in principle. One important difference is that pressure is an emerging quantity. So in the Navier-Stokes equation, you always have to solve an equation for the pressure in addition to this. In the kinetic gas theory, pressure just emerges from the velocity distribution. The entire thing is also exact with respect to their conservation. This is so mass, momentum, angular momentum, and energy, if you consider energy, which we usually don't, is exactly conserved. This is also related to the Navier-Stokes equation that we derive from this, comes out in conservative form. And in this conservative form, for example, you also get the right order, the physically right order of the differential operators. So for example, viscosity is in between two nablas, as it's supposed to be in the physical reality. That means so that if you have an tau that depends on anything, then the correct derivative will here, so the chain rule will automatically be fulfilled. So what else? There is two statements that are usually done is about the Boltzmann equation is here that all non-linearity is local and all non-locality is linear. This is different from the Navier-Stokes equation. So in the Boltzmann equation, you have this advection operator where xi is the particle velocity into f. So this is a linear operator, whereas the advection is a nonlinear operator in the Navier-Stokes equation. And this is also the non-local operation. Now, diffusion in the Navier-Stokes equation is, interestingly, diffusion is a linear operator in the Navier-Stokes equation, and in the Boltzmann equation, it is implemented through the collision operator, which is the nonlinear part. But here, this is a local operation. So the diffusion is here nonlinear, while in Navier-Stokes it is linear, and advection is linear. So this leads to all nonlinearity is local and all non-locality is linear, and the entire thing is as parallel as nature. And so there is a picture of about what we mean with how parallel this thing is, and maybe I hope I'm not too confusing here. So I have to discuss this a little bit. Again, this is so we are talking about past, present, and future. So how kinetic methods work in the Lattice-Boltzmann method in particular. So the Lattice-Boltzmann method works like physics. It's using a light cone. So suppose this red dot here is the position, or the position now and here, yeah, that you're interested in. And here again is the space coordinate, and here's the time coordinate. So this point is only dependent on the light cone, yeah, in the past, the converging light cone in the past, and it only has an effect on the diverging light cone in the future. So if you think about the incompressible Navier-Stokes equation, where you have to solve a global problem for the pressure, then you are of course very much aware that if you do this, that this one point here in the present depends on all the other points in the past, and all the other points in the future at any time will also depend on this point. So this, of course, means that information also has to travel through your mesh instantaneously. So now maybe you think, okay, so this is not necessary because there's also explicit Navier-Stokes solvers, so-called either compressible Navier-Stokes solvers or weakly compressible Navier-Stokes solvers, and they do something very similar to the light cone. Actually, they also have a light cone, but it's not quite completely the same thing. So because what is happening to this point, and I noticed this is very cartoonish, so bear with me. So what this does differently from the kinetic approach is that we always stratify. So we have a finite distance in which we do computations in space, but we always do them on one time level. Yeah, so we take our spatial derivatives, which are usually then on the right-hand side of the Navier-Stokes equation, and from this we compute a local time derivative, which gives us, taking say a Runge-Kutta scheme, gives us the future of this next node. And by this horizontal computation in one time level, of course, we also build something like a light cone, but this light cone is not completely symmetric. So in the Lattice-Boltzmann equation, this is a completely time symmetric operation, and this time symmetric operation has some certain interesting conditions and advantages. So because this is a symmetric operation in time, what you can do is you can do something that's called trunk splitting. So this trunk splitting, I don't want to go into detail unless you have questions later. This is you have two operators, a streaming operator and a collision operator, and what you do is you split one of these two operators, it doesn't matter which one, but I prefer to split the streaming operator. You cut him into one half before the collision and one half after collision. And the interesting thing about this is now your time your time step is symmetric in time. Yeah, because it is symmetric in time, it can only have even order errors because it's symmetric in time. So when you do the very stupid thing like Euler forward, like, you know, it looks like you're doing Euler forward. You have a one-step update. Yeah, but this needs to be second order accurate because it's symmetric. Yeah, so it cannot be first order or third order accurate. It can only be second, fourth, or sixth order accurate. So this leads us to accurate time integration. And what is also due to this light cone thing is, as you see, you have the same number of inputs to a collision that you have outputs to a collision. So you always have an end-to-end update. Whereas when you do finite differences, you reuse some of your data. Yeah, so you always access neighboring data for doing one finite difference, and you have to access the same data from the other point. So you have to recycle your data. In Lattice Boltzmann, this is not necessary. Yeah, you have just the distribution going in and the distribution going out. So you can immediately overwrite your input with your output, yeah, because you never need to recycle your input. So this has the consequence that we can do something that's called in-place streaming. So we just overwrite each time step with each itself. And because it only depends, each point only depends on itself, we can process everything in any arbitrary order. Yeah, so when we parallelize this on different computers, thousands of threads, there is no reason to do them in any particular order. We can do them all in parallel or in any other order that we like. Okay, so these are the consequences of the structure of the algorithm. And now we come to the Cumulant lattice Boltzmann method. The idea behind this is a little bit, okay, so this is of course Mr. Boltzmann, and we want to go from just a laminar Boltzmann to a turbulent Boltzmann, yeah? And this is, for this we need to investigate a little bit into the lattice Boltzmann method itself. So there are different ways of doing lattice Boltzmann. The one that is pretty common is the single relaxation or BGK collision operator, which is very straightforward. It just does streaming, collides the distributions. So yeah, it streams distributions and it does collision. And so the pictures that I show here is always roughly the maximum Reynolds number that I get with this kind of simulation at a certain resolution, which I believe was 500 grid nodes across the sphere. So then there is moment-based multiple relaxation time methods that get a lot more. So what you do here, you turn your distribution into moments and do the collision inside this moment space. And what we are doing here is using the Cumulant method, which is yet a little bit more complicated. We take central moments from the distribution, turn them into cumulants, do the collision, and then turn them back. So who ever heard about cumulants? So, and okay, so first I should probably first say what are moments. So moments, if you have a distribution function, a statistical distribution, you can take the Laplace transform and make a series expansion of this, and the coefficients of the series expansion, they are called moments. And the moments are actually identified with extensive quantities, so with density, momentum, and energy. And cumulants are a little bit differently defined, so there is a logarithm in between here, the logarithm of the Laplace transform of a distribution function. And this logarithm is here to make this these quantities that come out statistically independent of each other. And this is pretty interesting because what comes out of this, this is a very strange mathematical concept, but you all know cumulants, because cumulants, differences in cumulants are the things that make things happen. Yeah, cumulants are just velocity and temperature. Yeah, so if actually, and if you ask me for a definition, what is the simplest definition of a temperature? The temperature is the second cumulant of a velocity distribution function. That's the temperature. Yeah. So we know these things intuitively. We know them because differences in cumulants are the things that introduce that make fluxes happen. So if you have two different temperatures, yeah, so then there will be a flux of energy, not the cumulant. The cumulant is not flowing. Yeah, so the moment is flowing. Energy will flow from a body that has a different temperature, cumulant, than the other body, right? So, and now the Lattice Boltzmann, this Cumulant Lattice Boltzmann method, so it turns the distributions into these cumulants, and then it can relax all the cumulants with different rates. And this is possible because the cumulants are statistically independent of each other. So because they are statistically independent of each other, we can choose an individual relaxation rate or time scale for each of these moments. So why? Okay, so I have something in between here that I also wanted to address, maybe only as a teaser if it's of interest later, because Sebastian told me that I should include something like this. So in this cumulant, so because we have not only velocity and temperature, but we have more cumulants, in particular the cumulants related to the stress. So they carry additional information. So in the Navier-Stokes equation, of course, you have to compute your stresses, right? But you compute your stresses by finite differences or similar means from your velocity field. In gas kinetics, the stresses are independent variables from the velocities. So they do not, I mean, they are linked by their differential equation that you have to solve. But they're independent variables. So they carry additional information. And with using this additional information, we can do things smaller than one grid spacing. So we can use this for different things. For example, for doing cut cell boundary conditions. Yeah, so remember, we are on a Cartesian grid, yeah, but we want to have arbitrary structures, yeah, because our distribution carries information on the stress. We can use this information on the stress to do some subgrid scale interpolation and put boundaries of grids, so at any arbitrary distance q between grid nodes, for example. What we also have, so this looks a little bit busy, it's probably not well visible, but we can use this information from the cumulants to enhance interpolation of the velocity field. And this interpolation of the velocity field is important when we do grid refinement. Again, we are on a Cartesian grid, and you know we cannot solve any problem on a Cartesian grid unless we have some possibility to change the resolution. Yeah. So if we change the resolution, we have to interpolate. If we interpolate, we add dissipation to the system, but because we have subgrid information, we can mitigate this dissipation and actually get an accurate transition between velocity fields. And the last thing is we can use this, for example, for tracing a particle. What you see here is a trace line of a particle that goes very, very close to a boundary. So these are the lattice nodes, and it's not crossing the boundary. Yeah. So this is something that we've done many years ago. So what I actually wanted to say, why is it so important that we have different relaxation rates? So I'm a professor, I'm interested here in this mathematical stuff. I'm doing asymptotic analysis. So I'm looking into asymptotic analysis. Is you have a numerical method and you want to know the differential equation that it solves. Now this is of course stupid, you could say, because we already know what equation we solve. But we do not only want to know that we solve the Navier-Stokes equation, we also want to know what else do we solve? So what are the errors that we solve? So we can, with asymptotic analysis, we can derive a hierarchy of equations that we solve. The first one of which is, of course, the equation that we want to solve, our target equation, for example, the Navier-Stokes equation. And then we get the equations of the errors. And what we then want to do is we look at this equation of the errors and say, so if we are able to put these equations by the parameters that are somehow in our system, if we permit that these equations have a zero solution, that zero is a solution of that equation, then we can eliminate this error equation. So, and what we do here is we derive the equation of the leading error independence of all the free relaxation times in our system. Then we solve. So then we see there are different terms, so which usually depend on first order derivatives of velocity. And if all the factors to these terms, if they are simultaneously zero, then this error term is gone. And this is achieved by putting the free parameters in the numbers like this. And this turns a second order scheme that we had to a first order scheme. Yeah, so this is super convergence. And super convergence is, of course, the most effective thing that you could ever do in order to increase the performance of your code. So I mean, like you put things to a GPU and you buy a bigger computer and so on. This always gives you incremental increase. So this here gives you an orders of magnitude increase in performance. So there is this particular example that nobody was actually able to do before this in Lattice Boltzmann, yeah, because we have a Cartesian grid. And I'm completely aware that this is easily solved with open form if you set like a boundary elements, not boundary elements. I mean these boundary converging elements. Yeah, but remember, we are still on a Cartesian grid. We have nested Cartesian grids, but still we have a cut cell approach. And with this cut cell approach, it is very difficult to solve the so-called track crisis. So what is the track crisis? You're maybe familiar with this. So we have a sphere, and and here we have the track coefficient in regard to the Reynolds number, and what we expect is that at a certain Reynolds number of I guess 200,000, the track coefficient drops by 80%. Very suddenly, and the reason for this is that the transition point in the turbulent boundary layer goes from the front of the sphere to the back of the sphere. Yeah, so and then we have no longer a diverging wake, but a converging wake. And this is something that was very difficult to solve on Cartesian grid methods. And actually, all the turbulence models that we know, if you try to solve this problem, they will just kill this. Yeah, because they make the boundary layer too thick. Now with this super convergent cumulant lattice Postman method, so this is no longer a problem. Yeah, so this is how this came about. And now so there is no trick in this. So this is a simple no-slip boundary condition. There's no turbulence model in this. Yeah, the resolution here is 500 points across the sphere. But this is simply do it, solve it. No wall function, no turbulence model in this. Okay, so I have a few examples that I just want to click through. I don't know if because you said some of you have a time constraint. Yeah. Okay, so here this is urban ventilation. So we are civil engineers. This is something we are interested in. We have a 500 by 500 meter domain, and here is a measurement device, and this is in Basel, where they have measurements for this urban flow. And the good thing is that they also have the geometry for this, which is actually not completely watertight, but we were able to work with it. So this is the grid. So we use nested Cartesian grid. As always, we use cut cell, and we have periodic boundary conditions around this. And the resolution that we use, we have a coarse grid, fine grid, and a uniform grid. The uniform grid is at 1 meter. The fine grid, where's the fine grid? So the fine grid goes down to 0.5 meters. So this is the number of points that we have in these grids. Nodes, yeah, number of nodes, 41 million. And here's a coarse grid with the coarsest resolution is 1 meter. Okay, so there's some measurements on a tower. Yeah, so of the, let me see, this is the velocity profile, correct? So velocity profile. So there is a method, geometro is what is it? A spectral method. And here are the different Lattice Boltzmann solutions. There's also some turbulent quantities. So as you could probably imagine, the turbulent quantities for a coarser grid are a little bit smaller. Yeah, so this is how it is. So I have a little bit to apologize that I'm not the guy so much interested in performance. And actually, I was asked by Sebastian to talk about performance, but I have only this one slide about performance. So we were computing this. So this was only flow, no heat or something like this. So 2 hours physical time on the coarse grid. That is the one with a resolution of 1 meter. We get we need 0. So we need less than 1 hour, yeah, to simulate this. The simulation was done on an NVIDIA Tesla P100 with 16 gigabytes of memory. The fine grid was taking 7.5 hours, and the uniform grid was also not really real time. So the other method, where we actually don't know what was really the hardware, the other method took 5 days. Okay, so this is all I have on performance. What I can show you here is that we also did a simulation with some traffic. So here you see cars moving around, and they are emitting pollution, yeah, and the air is driving this pollution away. So here this pollution is driven to the north, and here the wind comes from this direction. So, okay, so if you're interested, so by the way, this was a bachelor thesis. Okay, I wanted to just briefly talk about acoustics, because this is also something that you can do with Lattice Boltzmann. So we have here built an organ pipe that we actually printed, so 3D printed. Just a little bit of theory of an organ pipe. So there is two frequencies that you have to meet up. So there's the edge tone, which comes from the jet hitting the edge, and then there's a resonance frequency of the actual body. Yeah, and usually you want to set the velocity such that the two meet. Or what you could also do, you can overblow, so then you get the next harmonic. Yeah, so you can, if you're familiar with musical instruments, for example, you play the horn. There's nothing that you can press there. Yeah, so you can blow, and then you can blow harder, and then you get the next overtone. So this is this is the way it's basically done. So we have discretized this very finely because we have to have the we have to resolve the edge here, otherwise we don't get the edge tone. So this is one of the most amazing crits that we've ever used. I think there was 11 or there was 10 levels of refinement. So this is the this is the fine grid, and then we have the entire room. Yeah, so with a very coarse resolution around it, and so this is now the comparison at the first microphone and the experiment. The experiment is this is the one that is recorded. You see the orange line, and the Lattice Boltzmann is the blue line. We have also the other microphone, and in the other microphone I have some sound, and I have to apologize that you are not going to hear this, but because I'm recording it, I will anyway press now the button. Oops, and it didn't work. See, press the button. Okay, so we didn't hear it. So we can actually make the sound audible, and my mother is an organist. She could identify what tone this is, and it's it's not sounding like a very very good instrument, but it sounds roughly like these plastic pipe that we actually printed. Okay, so this is a little bit the flow field. We had actually a velocity of 17 meters per second here. And now I'm talking too long, I recognize. Let me briefly come to some complex fluids. Just very briefly, so we are interested in simulation of fire. So this is a relatively complicated model for fire. The thing I'm showing later is a bit simpler. So we have oxygen, we have fuel, we have pyrolysis, temperature, and so on. This is how I did this here in this little two-dimensional example. The one that I'm going to show here just because it's the kind of the most beautiful video that I can offer, but the model here was much simpler than here. So this is a mixed is burnt model, and is actually not in Lattice Boltzmann. It uses a different kinetic method. It's using gas kinetic scheme, which is a little bit better in keeping track of the energy. But we can also do something like this with Lattice Boltzmann. Yeah, so this is okay. I cannot skip over this just because it's so beautiful. Okay, but anyway, because we are short in time, I guess I get going on. And we have also other complex fluids. We do in a bigger project here, the additive manufacturing and construction. We are in civil engineering. We want to simulate 3D printing of concrete. So we have here relatively complex method for multi-phase concrete model, where we have where the idea is that we want to solve for the air and the concrete. So most of these models that simulate liquid concrete only use the concrete and assume the air not to be existent. The problem is with additive manufacturing, you always get this inclusion of air bubbles, and they are weakening your final product, and so we actually want to simulate them. Okay, I'm not going too much into detail. If you're interested, you can ask me later about this. What we are doing is we're using a mixture actually of a phase field method and a sharp interface method. So because we originally came from phase field methods, but then we realized this doesn't work at such high density ratios. So we turned this in a sharp interface where we said, okay, there's a level set in this indicator function with 1/2, and then we put just velocity boundary conditions to the gas side and pressure boundary condition to the liquid side. And the interesting part of this is that this model is completely iteration free. It's completely explicit. Yeah, so no solving of no iteration here at the boundary or solving for the pressure boundary for the Poisson equation. So this is completely avoided. I have a very short video of a jet here. Yeah, what was it? Reynolds number 70,000. Okay. Now because we want to solve concrete, we have to add the complex viscosity part. So we have Bingham fluid. I have to introduce a Bingham stress. So this Bingham is just a Newtonian fluid with a yield stress. We implement the yield stress by computing an effective viscosity. This is usually done, but then there's an interesting special thing for Lattice Boltzmann, because in Lattice Boltzmann, viscosity is an emerging factor, is an emerging quantity from actually the mean free time, or the collision frequency. So you set the collision frequency, which is the inverse of the viscosity. Now, what you have to do is, in this model, you have to be able to set an infinite viscosity, which, of course, in the Navier-Stokes equation is always difficult to do. In Lattice Boltzmann, you have to set a zero collision frequency, which is much easier to do because I just said it's a zero, yeah, not to infinity. Yeah, so this is much easier. And here I have a toy problem. Here is not very serious because there are so many parameters that we are still work in progress. So now this is this. So what you see in the background is the vorticity. So you get this Bingham fluids put on top of each other, and then the thing will simply drop over, and it will briefly collide and bounce back a little bit. And now you see how much energy is in this solid part, because it's 1,000 times more heavy than the fluid. Okay. Yeah, that's what I wanted to say. So again, so kinetic methods are as parallel as nature, and you don't pay for it. You don't pay for kinetics if Newton's number is small and you use this asymptotic preserving methods. Then there's a lot of talk on Cartesian grids. They give you algorithmic efficiency, but you can only use this efficiently, the real overall efficiency, if you have nested grid, if you have subgrid boundary conditions, and of course, if you have superconvergence. So superconvergence is really making the difference. And yeah, so if you want to take a picture of this, we have a, this is probably not so interesting for industry, because this is GNU what is it? License, yeah. And we have our own open source Lattice Boltzmann solver. And now let me briefly stop here and let me see.